All right, here we go, our second lecture on endocrinology. We're going to start the R2A system today, and we're going to talk, because the R2A system has something to do with how SARS-CoV-2 kills us and affects humans. We'll look at that a little bit as well. So we're going to get a little deeper than into it. I don't think you know about Angiotensin 17, for example. So the R2A system. Now we need to review a little bit of the nephron, and we'll go over this again when we get to the principal cells, but this is the nephron, right? This is your very, very important for life. This is in your kidney. You have the glomerulus here, which is super important. That's part of the circulatory system in a way, because these are blood vessels in here. But remember, a lot of your sodium, your potassium, your chloride, glucose, all sorts of things get dumped into the proximal convoluted tubule. It goes through the loop of Henle. There's a thin portion and a thick ascending portion. What I'm concerned with today is this proximal convoluted tubule, and then this shorter distal convoluted tubule. The late part is called the connecting tubule, and then we have the collecting duct. So yeah, so you remember that from Dr. Doe. You've had lots of that, so I'm not going to go crazy into that. Just remember, though, this is an interesting system. Here's Bowman's capsule. That's the part that surrounds the glomerulus, which is, glomerulus is just a bunch of capillaries. But the weird thing about this arterial system is it's a double arterial system. We've never seen that before in the body. So we have blood flowing this way and flowing into a capillary system. These are the glomerular capillaries. Then it flows, a lot of the filtrate, which is made up of kind of blood fluid and everything I've already said. But some of it keeps going, and it goes down here, and then we have another, a peritubular capillary, which is where, like aldosterone, how it takes in sodium and water, follows. This is what we're talking about. This is where that goes, in this peritubular capillary. So a very strange system. This nephron has a double capillary system. These capillaries, by the way, are fenestrated, so that's the medium leakiness. I think I talked about that yesterday. Alright, so the R2A system, many AKAs for it. Some call it the RAS system, or the R2A system, the R2A. I tend to call it the R2A system. Officially, it's called the Renin Angiotensin Aldosterone system, which boards don't like to abbreviate, so you might actually see it written out as the Renin Angiotensin Aldosterone system. But you should know all these AKAs for that. This is arguably the most important controller and regulator of blood pressure, based on aldosterone and ADH mainly. There's other important functions with this as well, but it has a lot of function. But one of its major functions is to control sodium balance, sodium homeostasis in the body, and therefore that helps control blood pressure as well. It's via its regulation of sodium, it has these effects then, and we just said it controls blood pressure, blood volume, and sodium homeostasis. It's an incredibly busy system, as you may remember. It starts in the kidneys, but it involves the adrenal gland, all layers of the adrenal gland, including the medulla, which people forget about. Not only the cortex, but the medulla. Causes the release of, well, you tell me, how does it affect the medulla of the kidney? Good, somebody got it. It causes the release of epinephrine, right, which causes vasoconstriction of the capillary system underneath in the dermis. We'll get to that though. The heart and lungs are affected by this. The arterioles and venules, this is how it controls blood pressure, controls the smooth muscle, can contract smooth muscle of these members of the microcirculation. It has effects in the brain as well, can make you thirsty, etc. We're going to study it. The best way to study this is to give a hypothetical situation of someone just cut their hand and is bleeding really bad. And so we want to stop the bleeding or mitigate the bleeding and boost the pressure. Remember, if you're bleeding too much, you can't perfuse the body tissue. You run out of oxygen, and you can't give oxygen to your brain and your heart and your lungs, and you'll die. So the R2A system combats bleeding, or not only bleeding, but there's other things that can cause a drastic fall in blood pressure. That's what the R2A system is really designed for, as well as the sympathetics. I should say that regarding the sympathetic system, it's not really good at immediately stopping the bleeding. If you had to rely solely on the R2A system, you would be dead. Thank goodness for sympathetic outflow. That's what stops the bleeding quickly, while the R2A system has a more long-term and sustained effect than the ANS does. Remember, the ANS is there's a sympathetic and parasympathetic system. You should know that by now. The carotid sinus is an important structure. If it's activated by a fall in blood pressure, it will let sympathetic outflow out of the vasomotor center, and it'll contract all the blood vessels of the microcirculation, and it'll bolster your blood pressure and keep you alive, while other members of the R2A system kick into action, like aldosterone and ADH and things like that. How does the R2A system bolster blood volume in response to hypotension? Well, kind of mentioned it, but let's make it official. So it triggers the release of ADH, right? We know ADH already. It causes the kidney, the principal cells of the kidney, to conserve free water. Weird though, this is one instance where sodium doesn't go first, because remember, water usually follows sodium around like a puppy dog. But this case, no, it's free water, conservation of free water without sodium. If hopefully you know that by now, but that's a really general board physiology question. And what was the AKA that you don't know for ADH? Arginine vasopressin. It also triggers the release of aldosterone, which causes the principal cells of the nephron to conserve salt, and water follows. So that also increases blood pressure, just like ADH and aldosterone. They both cause increase of blood water, which increases the blood volume, which increases the blood pressure. It also, and most of these effects are angiotensin II, as we will learn. You probably already know that. But it triggers the thirst centers in the brain to make the person bleeding very thirsty, and they drink water. That's a weak mechanism, but it helps a little bit. It also causes flat-out vasoconstriction of the arterioles and venules, exactly like sympathetic response does. Sympathetic outflow is not a sustained, prolonged type of thing. It's an emergency thing that fades out after a while. But luckily, because of angiotensin II, we can also get a sustained vasoconstriction after the epinephrine, or after the sympathetic response fades away. The vasoconstriction, mainly by angiotensin II, will continue to keep those arteries in a state of vasocontraction. Stimulates the adrenal medulla, we said already, to release epinephrine, aka adrenaline, a little bit of norepinephrine, aka norepinephrine. Adrenaline, let's see, which one am I missing? Noradrenaline is the AK for that. I didn't put that in there. So those vasoconstrict as well to boost. But remember, these are targeted more for the skin, and these have more an effect on the skin. In the dermis, there's a capillary system and a venous system there that it shuts down there. It also, epinephrine stimulates the heart to pump harder and faster, because there's not much blood left, so you have to, what is left needs to be pumped around faster. What about an R2A system? Let's get into a little pathology now. That was pure physiology, but what about pathology? What about an R2A system that's always on? Can you think of a condition where the R2A system would always be on? Well, what if you have a failing heart, and therefore you would always have hypotension because there's not a lot of blood being pumped out of the heart. The R2A system senses that decreased blood pressure and is always on. And that ain't a good thing, as we will learn, because it can wreck the heart and it can wreck the lungs, and we'll learn more about that in the future. So, yes, aldosterone and angiotensin II have devastating effects on the heart. Let's see. Atherosclerosis, another thing that can turn on the R2A system beside a failing heart. What if you have atherosclerosis really bad and it's affected your renal arteries to the point your kidneys aren't getting enough blood flow? Well, if the kidneys aren't getting enough blood flow, that's going to set off the R2A system, which we're going to talk about that mechanism here in a second. But so therefore, those patients, if you don't get that kidney fixed, which sometimes you can't, the R2A system will always be on. All right, so let's take a little more close look at how this R2A system works. The story starts in the kidneys, and it's really turned on when the afferent arteriole of the kidney and a little bit of the efferent arteriole, they sense a decrease in blood pressure, or you could say a decrease in blood volume. That freaks them out. And when that happens, they release their hormone, which is called renin. So let's get a little deeper into that. Remember, the juxtaglomerular apparatus is the heart of the R2A system. It really involves two types of cells that directly and indirectly can stimulate the release of the hormone renin directly into the bloodstream. Right? Kidney has about 2.5 million of these little monitoring devices in each nephron throughout the kidney. And the members of this juxtaglomerular apparatus, these two cell types, are called the juxtaglomerular cells and the macula densa cells. Juxtaglomerular cells can directly release renin. They're the ones who make renin and release renin. These guys, the macula densa cells, I think Dr. Doe's talk about the mechanism. I'm not so concerned about that because we're not 100% sure of that mechanism. But they indirectly stimulate the juxtaglomerular cells. They kind of elbow these guys and say, hey, release your renin. But the key is to release the big R, the big renin. Okay? Simple question. What's juxtaglomerular apparatus includes what two cell types? Juxtaglomerular cells, macula densa cells. And here's where they live. So in the distal convoluted tubule, you can see that it goes right between the afferent and efferent arteriole. And if we blow this region up, there is the distal convoluted tubule, the distal tubule, aka. But you can see it's lined with these cells. These are the macula densa cells. And the afferent arteriole, here's Bowman's capsule, and here's the glomerulus, which is made of glomerular capillaries. And there the blood would flow this way. There's the efferent arteriole, and we can see instead of tunica media, we actually have a new cell type, which are endocrine cells. They release, these are not exocrine cells or exocrine glands, these are endocrine glands because they release their hormone directly into the blood, but they can release renin directly into the blood. So these guys and these guys are the juxtaglomerular apparatus. All right, so the juxtaglomerular cells, let's look at them more specifically. They are not chemoreceptors. They don't care about what's in the blood. They just care about pressure. So these are baroreceptors, just like the cells of the carotid sinus. And they're constantly monitoring the blood pressure. And if they sense a drop in blood volume or blood pressure, they freak out and secrete renin, their hormone renin, which is a protease. So it's going to cut something. And who does it cut before we get there? Good. Somebody remembered Angiotensinogen, which is secreted by the liver. But the release of renin is the rate limiting step. So how fast can you make angiotensin II? Or how fast can you make renin? or any member of the system? Well, this is the bottleneck right here. This is the rate limiting step. So the production of renin is the rate limiting step. So the juxtaglomerular cells are actually the rate limiting part of the renin angiotensin II aldosterone system. Isn't that interesting? What does renin do? Well, it's a protease, so it goes into the blood looking for its substrate or its mate. It wants to bind to somebody. That's the substrate. And its substrate happens to be something called angiotensinogen, which is a proenzyme. The gen means that it's an active form of an enzyme. But it's looking for renin. And renin chops off its tail when they bind together, just chops it off, and it creates a short form of angiotensinogen. And that short form has a different name, and that's called angiotensin 1. Right? So that's what renin does. It chops off angiotensinogen and creates angiotensin 1. Angiotensinogen, again, is secreted by the liver. It's constitutively secreted, meaning if you take a sample of your blood right now, it's always there. People with hepatitis, maybe their chronic hepatitis, maybe their R2A system doesn't work too good. Why? Well, one of the reasons is because the cells, the hepatocytes, don't make angiotensinogen very good. So they don't have much of a response. So they could start to have problems if they have a failing heart as well. They might have trouble with low blood pressure. All right, so as we said, the gen means it's a prohormone. So, okay, that's enough of that. Angiotensin 1 isn't really terribly exciting. We'll talk a tad bit about it in a minute, but it has no big role that we're interested in right now. It does do something. It floats around and it looks for its mate because it wants to be cut again. So it has a mate or somebody to bind with. And it's looking for somebody who's really important called ACE, angiotensinogen converting enzyme. Okay, this is throughout the body. You have ACE, but by far it's most prevalent in lung tissue. So on epithelial cells and the microcirculation, especially of the lungs, it lives, and it can hook up with angiotensin 1 and chop the back off angiotensin 1 and create a very active molecule, and sometimes a dangerous molecule called angiotensin II, the little Tasmanian devil, I call it. So as I just said, ACE converts angiotensin 1 into the very active and busy, sometimes dreaded, sometimes feared, sometimes deadly angiotensin II. Right? So it's definitely not a good thing to have too much angiotensin II around. Angiotensin is on the loose. Let's talk about it a little bit. So I just call it AT2 or angiotensin II, angiotensin Roman numeral 2. In the boards it'll be called angiotensin Roman numeral 2. Amongst its functions, one of the most impressive functions is its ability to cause vasoconstriction of the microcirculation. It's a very, very strong, the most potent vasoconstrictive agent. And because it's a vasoconstrictor, it's called a pressor agent. Pressor agent. The way I remember that is vasopressin, or arginine vasopressin. Remember, that's an AKA for ADH, antidiuretic hormone. Pressor agent, so it, just like ADH does, it causes the reabsorption of free water, which would raise blood pressure. So a pressor agent raises blood pressure. Or you can think of a bench, somebody doing a bench press. This is why I don't draw. But there's a barbell. So somebody is doing a bench press here, pressing this barbell upwards. So pressor means to go up with blood pressure. Okay, angiotensin II can't do anything unless it binds with its receptors. So its receptors are really easy to remember. They're called angiotensin II receptors. And where are the angio 2 receptors? They are ubiquitous. They're everywhere. They're in microcirculation all over the body on endothelial cells. They're in heart tissue, is not a good thing. There's a lot of them in lung tissue, which is not a good thing. They're in the intestinal tissue as well. They're in the brain. They're everywhere. They're ubiquitous. But these are the main: the heart, the lungs, the intestines, and the venules. They're not in the capillaries. I probably shouldn't have that in there. But they're in the arterioles and the venules. Okay, so what does angiotensin do? Oh my God, we're going to be talking about that next week as well. But they vasoconstrict, right? Because remember our scenario, our person is bleeding, so they do hit the arterioles and venules. They're a potent pressure agent, and they, by squeezing the pipes and closing the diameter of the blood vessels, it's going to increase the blood pressure. They also, if there's too much angiotensin II around, they can cause vasodilation of the capillaries. So the capillaries can actually start to leak too much blood fluid out, and you can get a overwhelming of the blood fluid, which is called swelling. If that happens in the alveoli, it's not called swelling, it's called pulmonary edema. So they can cause that. They also, if too much angiotensin is around and the tissue has receptors for it, it causes a proliferation of cells in that tissue, like heart tissue can become too muscular, and it can call in fibroblasts as well, and you can get a scarring and a proliferation of that tissue, which is not a good thing. Same with the alveoli, as we'll see here in a minute. You don't want scarring to happen in your alveoli, or those alveoli won't work anymore and you can't breathe. It also causes a hypercoagulable state in the microcirculation if there's too much of it. We're not exactly sure how that one works. It's possible it could increase von Willebrand factor. We'll also talk about COVID-19 and CVPP, cardiovascular and pulmonary pathology, which is a companion course to this, which you have this, almost all of you have this quarter as well. So we'll talk about that, but it does make a hypercoagulable state, which is not good. What does that mean, hypercoagulable state? That means that you're going to get blood clots, and you may or may not know that's what's killing people with COVID-19, as people have tons of blood clots on autopsy in their lungs, their heart, their brain. Makes the blood very, very clotty, amongst other things. So a chronically activated R2A system, if someone has a failing heart, that is not good. We have to, not only does it fix the blood pressure, but it goes too far. So people with a failing heart often have hypertension because of the chronically turned on angiotensin II, and it corrects the blood pressure and then some and gives you hypertension. But yeah, so same thing. It can wreck your heart and lungs because of cell proliferation and scarring of those tissues. It can cause blood clots in the lungs and the microcirculation in the brain, and you name it. Any tissue can be affected, especially the lungs. And it can cause pulmonary edema. Those aren't good things, and that's what's happening in a way to COVID-19 patients, some of this stuff, and we'll look exactly how that works. Let's talk about angiotensin II, and we'll come back to the COVID story in a minute. Our angiotensin III is another one. It has a similar effect to angiotensin II. It can, like for example, just like angiotensin II, angiotensin III can trigger the release of aldosterone. It's made from angiotensin I, so even though angiotensin I doesn't do anything, it can be converted by aminopeptidase A into something similar to angiotensin II, which is angiotensin III. And so we'll leave it at that for right now. Let's finish, though, before we get into this COVID thing, let's finish up the juxtaglomerular apparatus. We haven't talked about the Macula Densa cells yet. Remember, they live in the proximal portion of the distal convoluted tubule, aka the distal tubule. They are very close to the juxtaglomerular cells, as I showed you already. They are the second member of the juxtaglomerular apparatus. Who is the first member of the juxtaglomerular apparatus? Juxtaglomerular cells. They are not a baroreceptor like the juxtaglomerular cells. These guys could care less about pressure. These guys are osmoreceptors, aka chemoreceptors. They have their little receptors, little snake. They're like little snakes. They have this little tongue, and it's tasting the filtrate for sodium and chloride concentration. Here they are again. So they're right here. We have already looked at that picture. There's the big picture where they are. But yeah, there's the Macula Densa cell. It has like a snake's tongue is constantly tasting the air. This is the fluid though, right? This would be the distal convoluted tubule, and it's tasting for chloride and for sodium, making sure that the concentration is just right. If it drops, they don't like it if it drops. So constantly tasting. All right, so how does this work now in our bleeding response? A person is bleeding. Well, if you're bleeding, your blood pressure is going to drop. And well, I thought the pressure will drop inside the loop of Henle and the distal convoluted tubule. The whole nephron pressure will drop a little bit. But how does that work? Because what's that got to do with sodium? Well, here's the story here. So the cells of the proximal convoluted tubule, which by the way, remember from Dr. Doe histology days, they're simple cuboidal cells. What's weird about them is they do have a brush border, a very tiny brush border. But their job is to pick out the sodium and chloride amongst other molecules. Their job is to return that back into the blood. For whatever reason, the glomerular capillaries are like leaky sieves. They dump all sorts of stuff into this filtrate, and it's not good. It needs to be immediately sucked back out. And so all these cells do that. They suck and pick out sodium and chloride, and then water will follow. But there's a certain speed that the filtrate moves through here. And at a normal speed, they can only pick out so many sodium molecules. But if you have hypotension and there's not a lot of pressure, it slows down the river flow here. And these cells, these proximal convoluted tubules cells, can pick out too much. They have too much time. So they pick out too much sodium and water, which decreases the concentration. My classic example. So here's proximal convoluted tubule cells, like someone working on a conveyor belt. So these workers, conveyor belts going that way, their job is to pick out the bad potatoes, but they can't get all the bad potatoes because the conveyor belt's moving along and they have a quota to make. But if you slow that way down, they can pick out every single bad potato. The bad potatoes will say are the sodium, so they pick out too much if your blood pressure drops, and that's going to drop the concentration of sodium. And by the time the filtrate gets to the little snake tongue, the snake tongue says, whoa, there's no sodium and there's no chloride. It freaks out. We won't worry about the mechanism, but it elbows through mechanisms that are still not completely understood. It elbows these juxtaglomerular cells and says, hey, we got a problem here. The sodium levels are really, really low, and we need the conveyor belt sped up. So it tells its buddy to release renin into the bloodstream. Its buddy are the juxtaglomerular cells. So key test question. So these macula densa cells, do they directly release renin or indirectly release renin? They indirectly release renin. They have to signal their buddies, the juxtaglomerular cells, to do that. Okay, got it? All right, everything I said, renin's released and then goes through the same the same details. The renin converts Angiotensinogen into Angiotensin I, which is converted by ACE to the dreaded Angiotensin II. So now let's go back to the SARS-CoV-2 story, the COVID-19 story a little bit. So to understand COVID-19 disease, we need to go a little bit deeper. So the R2A system actually has two units, or two divisions, or two arms, the researchers typically call them. There's the pressor arm, which stars angiotensin II. Okay, we've talked about it and its effects already, how it causes vasoconstriction and it can negatively affect the heart and causes some nasty stuff if there's too much of it. But then there's one we haven't talked about. There's an called the anti-pressor arm. And the star of the show is maybe an angiotensin you never heard of. It's angiotensin 17. You should really call it, though, angiotensin 1-7. And what's its basic job? Its basic job is to soak up excess angiotensin II. So that's one thing it can do. It can also bind to its receptors on cells. They're called MAS receptors, MAS receptors, and it stimulates just the opposite effect of angiotensin II. So it relaxes tunica media and vasodilates instead of vasoconstricts. It turns off the proliferation effect that angiotensin II has in the heart and in the lungs. It basically does the opposite of angiotensin II. Okay, so it soaks up you can't soak all of it up. That wouldn't be good to soak all of it up. But it soaks up angiotensin II and reverses the deleterious effects of too much angiotensin II. Who makes it? So this is important. Who makes angiotensin II? And it gets confusing. Who makes angiotensin II? Who makes this? What do you mean makes it? Isn't it just floating around? No, right? It's got to be made. Remember, ACE, angiotensin converting enzyme, makes angiotensin II. Okay, great. It's in all over the body, but it's mostly in the respiratory system. Who makes angiotensin 1-7? It's another ACE, but this one is called ACE2. And it's another enzyme that is everywhere in the body as well. Everywhere there's ACE enzymes, there's ACE2 enzymes. ACE2, there's even some more. It's even more prevalent than ACE. But just think of them as side-by-side neighbors. And then who's the substrate? Where does angiotensin 1-7 come from? It comes from angiotensin II. I think we said that already. Angiotensin II can be converted into a very healthy enzyme called angiotensin 1-7. So that's where it comes from. ACE2, so ACE2's main substrate is angiotensin II, and it soaks up. Thank goodness normal people don't have tons of angiotensin II around because it gets soaked up by these ACE2 receptors. Okay, so that's a good thing. It's sometimes a member, there's an axis, there's an angiotensin 1-7 ACE2 MAS axis, because these are the receptors. There's the enzyme, and angiotensin 1 is the end product. Angiotensin 2 is converted into angiotensin 1-7. Angiotensin 1-7 binds to MAS receptors, which would be on, let's say, a heart cell or a lung cell. Got it? All right, where does it bind? We already said it binds to MAS receptors. And binds to the same tissue the angiotensin II does. Specifically, you should know where it binds, because this is COVID-19, can affect all these tissues. The lungs, probably the number one spot. The heart, the intestines, the endothelial cells of blood vessels, especially the arterioles and venules. The nasal cavity, the pharynx, the oral cavity, entire pharynx, including the nasopharynx, the laryngopharynx, the entire pharynx, and even the eyes, right? Cover the eyes, right? Why do we have to wear shields in lab? Because there's there's receptors. There's angiotensin 2. There's ACE2 receptors in the eyes, and that's where COVID can bind. I spoiled the surprise. You probably already know that though. And there's even some in the brain. So although its main substrate is angiotensin 2, we said angiotensin 1 doesn't do much. Here's another thing it can do. It actually can bind and be converted into angiotensin 1/7, but it doesn't happen very much. So, but there is another thing that angiotensin can do. I think Guyton says angiotensin 1 does nothing, but that's not true. It can do some stuff. All right, here's the historical data of angiotensin 1/7. We learned about it way back in the 80s, but hasn't until COVID popped up. We haven't really heard that much about it, and now we're hearing about it a lot. So there's Marshall Dillon. That was an old Western that was popular. Used to watch that when I was a little kid. He's a good hero, good values, kept peace in Dodge City. That's angiotensin 1/7. It's a good guy. It has the opposite effects of angiotensin 2. What are those effects? So it vasodilates. Remember, it has to bind to the MOS receptor though to do that. It has anti-inflammatory properties, which is awesome. It has anti-proliferative properties, so it discourages heart cells from dividing and becoming too thick and scarred up. It has anti-fibrotic action and anti-thrombogenic action, so it discourages blood clot formation as well. So very cool. So how does SARS-2, and that's of course again the virus that causes COVID-19 is SARS-2. It uses ACE2. That's how it gets into the body. SARS-CoV-2, the virus that causes COVID-19, it binds to ACE2 receptors, and it swallows. Once the SARS-CoV-2 binds to ACE2, it is taken inside the cell, and then the virus replicates like crazy. It's an RNA virus. I'll let Dr. Doe, I don't know if he's getting into this or not, but he can get into that more. It is an RNA virus, but I mean, there's a problem here. Anybody see a problem? Well, if SARS-CoV-2 binds to ACE2 receptors and it starts knocking out R2 receptors, how is angiotensin 2 going to be converted to angiotensin 1/7? That's a problem, right? So people with COVID-19 have decreased levels of angiotensin 1/7. Marshall Dillon's kind of left out in the cold, and that's not good. Now we have angiotensin 2 running wild in people with these infections. And so that's starting to cause problems in the lungs. It's pro-inflammatory, angiotensin 2 in high volumes too, so it stimulates an inflammation. I mean, the virus bound to cells within the lungs and in the heart and everywhere else, that causes an inflammation in and of itself. But now you got angiotensin 2 running wild in the area as well. And that's going to kind of stir the pot and spark the inflammation even more. So that's not good. Yeah, so ACE2 receptors are occupied. You can't bind angiotensin 1/7, and therefore, I mean, you can't make angiotensin 1/7. Let's see, did I mess something up? If it binds ACE2 receptors, no, that's right. If it binds ACE2 receptors and they're occupied, then you can't take the angiotensin 2 and make angiotensin 1/7. Therefore, angiotensin 2 runs wild, and you get things. This is the big one, right? That's what's killing people. Pulmonary edema, fibrosis. You can't breathe if you get pulmonary edema, right? Your alveoli fill up. And we'll look at that here. Actually, we'll look at it right now. So as the virus gets into the alveoli, they become inflamed. Your body sees it, and a wicked inflammation occurs. So blood fluid from the inflammation and remember, it increases capillary permeability as part of the inflammatory product, and angiotensin II can help with that as well. So you got blood fluid leaking into the alveoli, and if that's not enough, the inflammation and the angiotensin II can cause scar tissue formation. On autopsy, they feel, you don't need to know this, but they find hyaline tissue inside the alveoli, which completely block the alveoli from gas exchange. So yeah, the alveoli is knocked out. The patients become hypoxic. They have to go on respirators, and they eventually die of asphyxiation. At first, a pneumonia starts, and some people don't get very sick, and they get a little pneumonia. Pneumonia means that only one part of the lung has been affected. If you get an pneumonia in the entire lung, you don't call it pneumonia anymore. You call it ARDS, or acute respiratory distress syndrome. This is what's killing COVID patients right here. If they get basically a pneumonia of the entire lung, it's too much inflammation. All right, and remember the tracheobronchial tree, of course, and just like a tree, we have leaves. Those are the alveoli. That's where, there's a blood vessel coming by here. It dumps off CO2, and oxygen has to be passed into these things. They're just like the leaves on a tree. Like this beautiful tree. This half of the tree is alive. What happens if you pick all the leaves off the tree? What happens to the tree? Looks like this. It dies. What happens if you destroy all the alveoli with a wicked inflammation? Well, you die, because you can't get oxygen passed from the air into your bloodstream anymore, and your tissue can't get oxygen, and you die. That's basically what's killing people. And if that's not bad enough, to make things even worse, there's cytokines. Some patients are having cytokine storm. They're hanging on the respirator. The respirator is forcing air into these damaged alveoli and forcing air into the blood. But you can get so many cytokines released from the lung tissue that it starts affecting the liver and the kidneys and the heart. COVID patients have developed carditis, inflammation of the heart, and there's no COVID infection in the heart at all. It's just from cytokines, which is like gasoline, like tumor necrosis factor alpha is one of the strong pro-inflammatory cytokines. It's floating around the body, and it's landing in organs and causing an inflammation where there's not even anybody invading, and therefore you're wrecking organs. And for some reason, if your lungs are still functioning, you could die of heart failure, or kidney failure, of liver failure. It could get into your brain. So cytokine storm is a very serious complication of COVID-19. All right, just some of the research interesting. This angiotensin 1-7 MAS receptor, in people with COVID, they're trying to figure out a way to activate these MAS receptors. We can't activate them. How come you can't activate them in someone with COVID? Because the ACE2 receptors, which make angiotensin 1-7, are shot. The COVID virus has blocked them, right? So those are out. But if we can bypass that and stimulate the MAS receptors, that can undo some of the deleterious effects of angiotensin II, cut inflammation, cut blood clotting, things like that. So they're trying to find MAS agonists is a big area of research right now. Okay, hoping that over. See you guys later.